A substation fault lasts less than a second, but in that second, thousands of amperes surge through the ground beneath your feet. If the earthing system is not designed adequately, that energy has nowhere safe to go and it will cause a disaster. Hey everyone, my name is Sahil, and in today's video, you will learn everything about substation earthing, from the basics of what a substation is and how the earth grid works, to the risks like touch and step potential, ground potential rise, and grid impedance. We will discuss how a system is designed, what to do when a design falls short, and how it is tested, verified, and a lot more. You can find all of that in this book, Our Substation Guide. We'll talk about it a bit more later. Think of this video as a crash course on substation earthing. By the end, you will have a complete picture of how this process is built and everything that affects it. But why should you listen to me? At Axis, we've been manufacturing earthing and lightning protection systems for more than 30 years. From earth rods and to earth mats, our products are installed in substations, solar plants, utility scale applications, and much more across the world. So let's start with the basics. What is a substation? A substation is a point in the power system where voltage is transformed, controlled, and distributed. Think of it as the gateway between the high voltage transmission network and the end users who consume the power. Now, within that substation, every metal structure and every piece of equipment needs to be connected to the earth. This is done through a process called substation earthing. When a fault occurs, it gives that fault current a safe and controlled path into the ground, protecting both the equipment and the people working around it. Now, the substation earthing system is built around one core component, the earth grid. The earth grid is a network of conductive materials, typically copper or galvanized steel tapes, buried beneath the substation. It connects every piece of equipment to a common grounding point. It serves two purposes. First, it carries fault currents safely into the earth during fault conditions, preventing dangerous voltage rises within the substation. Secondly, it protects personnel by keeping all equipment at the same electrical potential, minimizing the risk of electric shock through touch and step potential, ground potential rise, and grid impedance. Now, let's understand these risks in detail, starting with touch and step potential. If you touch a conductor while standing on the ground, the current travels through your body. This is touch potential. If your feet are apart, voltage differences between them drive current through your body. This is step potential. The tolerable touch voltage for a person of 50 kg of body weight is calculated using this formula. Similarly, the tolerable step voltage for a person of 50 kg body weight is calculated using this formula. Both depend on two key factors: the resistivity of the surface material and the duration of the shock current. Longer exposure and lower surface resistivity make the situation more dangerous. If touch and step potentials exceed the tolerable limits, the current passing through the body can cause an irregular heart rhythm that can be fatal. The risk is higher for touch potential because the current path runs through the chest and directly affects the heart. However, these risks can be controlled. The earthing system is designed to keep touch and step voltages within the tolerable limits. If the design falls short, there are several ways to bring those values down. You can increase the density of the earth grid. You can add more earth electrodes. You can treat the soil to reduce its resistivity. Or you can lay a high resistivity surface layer like crushed rock in the yard. This increases the contact resistance under a person's feet and reduces the current that flows through their body. Now, touch and step potential do not appear out of nowhere. They are driven by something called ground potential rise. Before we understand ground potential rise in detail, please subscribe to our channel for more insightful videos on electrical engineering. We also have this detailed guide on the topic of substation earthing. You can download it for free by clicking the link in the description. When a fault occurs, a large current flows from the faulted equipment into the earth grid. That current combines with the resistance of the grounding system and this causes the entire earth grid to rise to a higher electrical potential than the surrounding remote earth. This rise in potential is what creates the voltage gradients responsible for touch and step potential. You can calculate the ground potential rise using this formula. But what happens if you get it wrong? If GPR is too high, the voltage gradients across the substation yard exceed safe limits. Touch and step potentials become hazardous and the protection systems can malfunction. Any telecommunications or control cables leaving the substation carry that elevated potential with them, and this creates risks far beyond the substation boundary. So how do you fix it? To bring the ground potential rise down, you need to reduce either the grid current or the grid resistance. Reducing grid resistance is the practical approach. It is done by expanding the grid area, by adding more electrodes, increasing the depth of the grid conductors, or treating the soil to lower its resistivity. All of these measures increase the ability of the earthing system to dissipate fault currents safely into the earth. Finally, let's move to the last risk, grid impedance. When the fault current tries to flow through the earthing grid into the soil, the grid does not let it happen freely. It opposes that flow, and that opposition is called grid impedance. It has two components. The first is resistance, which is a property of a material that opposes the flow of current. In the context of the grid, it comes from the conductive materials used and the contact between the grid and the soil. The second is reactance, which is the opposition that arises from the magnetic and electrical fields created around the grid and soil. If grid impedance is too high, GPR rises to dangerous levels during a fault, leading to hazardous touch and step potentials across the yard. A high grid impedance also causes uneven distribution of fault current, with high current densities concentrated near the fault location, resulting in localized heating and damage to the grid itself. To reduce grid impedance, increase the grid area, add more conductors, increase the depth of burial, or reduce the resistivity of the surrounding soil. All of these measures lower the opposition the grid offers to the fault current, keeping GPR within safe limits. Now that you understand the risks, let's look at how a substation earthing system is actually designed. The process follows 8 steps, and it starts with soil resistivity. Before any earthing system is designed, the first thing you must do is measure resistivity at the site. So what exactly is soil resistivity? It is the measure of how strongly the soil opposes the flow of electrical current. The lower the resistivity, the easier it is for the current to flow into the earth, making your earthing system more effective. The higher the resistivity makes it harder for the current to dissipate and difficult to achieve a safe earthing design. If soil resistivity is not measured accurately, the entire earthing design will be built on wrong assumptions. The grid resistance will be miscalculated, GPR will be underestimated, and the touch and step potentials across the yard may exceed safety limits. We have a detailed video showing how to measure soil resistivity using the Werner 4-pin method. The link to that video is in the description. Next, let's measure the fault current. With the soil model in place, the next input the design needs is fault current. This is the abnormally high current that flows through the substation during a fault condition, such as a short circuit or a lightning strike. It is not a value you design for today, it is a maximum fault current expected over the entire lifetime of your substation, including any future expansions. In practice, the fault current is not something you calculate from scratch. It is determined by the rating and impedance of the transformer at that substation, and it is typically provided by the equipment manufacturer or the utility. This value then becomes a direct input into your GPR calculation and conductor sizing. Now, let's calculate conductor sizes. With the fault current known, the next step is sizing the conductors that will carry that current safely through the earthing system. The conductor needs to be selected based on 3 properties. Firstly, its current carrying capacity. Secondly, the thermal capacity per unit volume. And thirdly, its resistance to corrosion. If the conductor is undersized, it will not survive the fault current. It will heat up, degrade, and eventually fail, leaving your earthing system compromised exactly when it is needed the most. With the conductor size, we move to steps 4 and 5 of the design process: selection of the ground electrode and the ground grid. The conductors are embedded into the earth as ground electrodes, which collect and dissipate fault current into the soil. These electrodes are then interconnected across the substation to form the ground grid, which is the physical backbone of the entire earthing system. With the ground grid in place, the design moves into analysis, steps 6, 7, and 8, which involve touch and step potential analysis, ground potential rise analysis, and grid impedance measurement. They've already covered each of these in detail in the risk section of this video, so you can watch it back there if you want to refresh yourself. After all this analysis, you run these calculations against the actual grid design to verify that everything stays within safe limits. If it does, the design is complete. But if it does not, the grid needs to be revised. But what happens when the design does not meet the safety limits? This is where mitigation strategies come in. When you conduct the soil resistivity test, the data reveals how resistivity varies at different depths. In most sites, the soil is not uniform. It exists in layers, each with a different resistivity value. The mitigation strategy you choose depends on which layer is more conductive. If the second layer soil resistivity is lower than the top layer, add more electrodes. This drives current deeper into the more conductive soil, bringing grid resistance down. If the bottom layer has lower resistivity or a water table is present, increase the length of the electrodes. This pushes them deeper into the more conductive zone. If the top layer soil resistivity is lower than the bottom layer, increase the density of horizontal grid conductors. This creates a denser mesh that spreads current more effectively through the conductive upper soil. If space is available, increasing the overall grid area reduces grid impedance directly, since a larger area means more soil contact and lower resistance. And if the soil resistivity itself is the problem, the material around the electrodes can be replaced with an earth-enhancing compound, such as this, which reduces the contact resistance between the electrode and the surrounding soil. These strategies bring the design within safe limits, but once the system is installed in the field, how do you know it is actually performing as designed? I'll give you 3 tests which will help you identify this problem. The first is the ground impedance measurement, which measures the total resistance of the earthing system to remote earth. It gives you a direct estimate of the GPR the system will produce during a fault. The second test is the touch and step voltage measurement. A known current is injected into the ground grid from a remote electrode, and the resulting voltage gradients are measured across the yard. The actual touch and step voltages are then determined by scaling up for the full substation fault current. The third test is the integrity test. This test verifies that all connections are sound and checks for broken conductors, high resistance joints, or any damage to the grid that may have occurred during construction. Lastly, do you know where these tests, formulae, and procedures actually come from? They come from 3 key standards that govern everything that we have discussed in this video so far. First of all, IEEE 80 is the primary international standard for substation earthing design. It establishes safe limits for touch and step voltages, provides a structured design procedure, and defines the analytical methods used for GPR and grid impedance calculations. While IEEE 80 is the global standard for substation earthing, you will always have local codes and local standards that are as per your requirements. In India, we have IS 3043, which is the Indian Code of Practice for Earthing. It provides guidance on earthing methods for land-based electrical installations in India, covering everything from system earthing to equipment earthing across different supply configurations. In India, we also have the CBIP Manual, which is published by the Central Board of Irrigation and Power and is specific to AC power systems in the country. It covers earthing design, field installation practices, monitoring, maintenance, and performance testing for substations and HVAC outdoor stations. Together, these 3 documents form the regulatory and technical foundations for substation earthing design and installation in India. But there will be different regulations in each country. This now brings us to the end of the video. We have a detailed guide on the topic of substation earthing. If you want to learn more or you want to go deeper into the subject, please click on the link in the description and you can download it for free from our website. I hope you now have a clear understanding of substation earthing, all the way from understanding the risks to how to design the system, how to verify it in the field, and knowing which standards govern every step of the process. At Axis, we have a team of 50 plus engineers who design, install, and test earthing and lightning protection system as per all the required standards globally. Our products have been used in substations, data centers, factories, and even in everyday residential and commercial buildings. If you found this video helpful, please give it a like and subscribe to our channel for more insightful videos on electrical engineering.